Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to summarize everything we've done in this course. It's been a long journey to this point, because not only have you had to study deep learning, but you've had to study reinforcement learning as well. This course was about combining these two techniques, and also a little bit about expanding our knowledge of reinforcement learning. I tend to think of this as applying deep learning to reinforcement learning, rather than the other way around. Deep learning is more like a general technique that can be applied to supervised learning or unsupervised learning as well as reinforcement learning. But reinforcement learning is an entirely different paradigm, where we have an intelligent agent trying to maximize its reward in some environment. So what did we learn in this course? Well, we started this course with a review of some basic techniques in both reinforcement learning and deep learning. We looked at Markov decision processes and the three ways of learning how to solve MDPs: dynamic programming, Monte Carlo methods, and temporal difference learning. Next, we looked at the OpenAI Gym, which provides us many environments for practicing reinforcement learning. This is especially valuable because coding our own environments would be extremely time-consuming and completely unrelated to reinforcement learning itself. This allowed us to practice the reinforcement learning techniques we just reviewed and to practice using Theano and TensorFlow, which are very helpful because of their automatic differentiation capabilities. They let us build arbitrarily complex neural networks, and the update equations are all automatically generated from the structure of the cost function. Also in this section, we looked at a special type of neural network called the RBF network. Unlike our usual deep neural networks, these networks are shallow and use fixed feature representations. That means features won't be learned using gradient descent. Next, we looked at n-step methods and TD lambda. We saw how these are both ways we can do something that's kind of in between Monte Carlo and TD learning. Whereas n-step methods are discrete, the lambda in TD lambda is continuous and between 0 and 1. Now, of course, there's nothing that makes these better or worse than the existing reinforcement learning methods we learned about. They are just new hyperparameters to be chosen. Next, we looked at policy gradient methods. This gave us a totally different way of solving reinforcement learning problems. Instead of making the policy just greedy or epsilon greedy with respect to Q, we parameterize the policy itself. In this situation, we parameterize both the policy and the state value function v of s. Parameterizing the policy is interesting because it allows us to easily handle continuous action spaces, as we saw with continuous mountain car. The only change we had to make was, instead of modeling the output as a discrete distribution, we modeled the output as a Gaussian. Lastly, we looked at deep Q learning. Deep Q learning is just the combination of deep learning with reinforcement learning. Initially, deep learning looks like a pretty attractive option in reinforcement learning, because we already have the theory behind approximation methods, and neural networks are function approximators. So a naive approach would be to just plug in a neural network. Of course, this doesn't work, so we learned about new techniques to make it work. In particular, we looked at experience replay using a target network and combining previous data into the current state in order to model motion. Now, of course, this isn't all there is to deep reinforcement learning, since new stuff is being invented all the time. Could new material be added to this course? Most certainly yes. I love giving you guys free updates to my existing courses and making them better over time, so feel free to use the Q&A to make recommendations. Thank you for taking this course, and I'll see you next time.